street. Okay. So still talking about that HR diagram, Hirschsprung-Russell diagram, that has kind of that main sequence, and we have a scatter of important stars here, and then kind of what we call white dwarfs down at the lower left-hand corner. Let's see. So stars actually kind of move around on the HR diagram. This is, I guess this only works this way. Basically, when they arrive at the main sequence and they tick, 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 and that's that kind of diagonal of stars, they stay there. Our sun is going to stay there for another about 5 billion years. It's been there about 5 billion, so that's another 5 billion, 10 billion sort of deal. And then it's going to leave the main sequence and kind of migrate up here in the red giant sort of area. Okay, and actually I think we heard that on the last video we watched about the sun. So that's when we say it moves on the HR diagram. It's moving. When our sun does that, it moves. It's going to basically become more luminous because it's moving up. Okay, those things are more luminous. And there's a chance it might even be a little cooler. Okay, and we'll talk about why that is. But it moves on the HR diagram. Okay, so giant, actually the next stage for our sun is the giant stage, a red giant. There's kind of, to me, a subtle difference between red giants or red supergiants, okay, but they're all kind of up there in the HR diagram. So this actually is showing you exactly what that video kind of talked about, about our sun. It said our sun is going to swell. This is showing a star swelling, okay? So there we go. So I think you guys might have a homework question. It might not be for this chapter, but might be for the next chapter, talking about how do we use an HR diagram to kind of show how a star is changing. And it will literally move because it's changing its luminosity and its surface temperatures. Well, this is kind of a cool sort of a side topic. We're going to talk about how stars are born. In the video we watch here in a minute, it's going to talk about how stars are being born. But oftentimes stars are born all kind of at the same time. And you know, if you were like, go to an OB ward where they have the little babies in there, okay. So basically it's a place, there are pockets of material out there where little baby stars are being born. So there's two types of clusters then. There are open clusters. This is an example of the Seven Sisters. It's got a whole like little folklore with it. But can you see where sometimes people look at the Seven Sisters with binoculars and they swear it looks like a little dipper. It does kind of. Doesn't look like it's a bowl here, kind of a handle here. Looks like, but it's like this big in the sky. That actually, the Seven Sisters is in the constellation Taurus. Taurus the bull. Okay.
Which seven is it?
Yeah. And that's the other thing, and actually I think I have a slide maybe later, but there's definitely more than 7 there. It's the brightest ones that you see with the naked eye, yeah. There's definitely more than 7. But these would all be born about the same time, okay? Now, good chance that there's some of those like little dimmer stars hiding in that goop. They're being outshined by the few brighter stars. But can you see kind of the cloudy stuff here, okay? This actually is an open cluster with nebulosity. Sometimes you'll be reading about something you can see in the nighttime sky and they'll say it has nebulosity. Well, what's a nebula? Nebula is basically kind of dust or gas or clouds in outer space. Space stuff, space junk, yes. Okay, so that's an example of an open cluster. Globular clusters are like this. And all globular clusters, a few things about globular clusters. They definitely have, open clusters are just random. Globular clusters are like a ball, okay? Some globular clusters have a lot of stars in them, some are kind of more sparse. But the thing about globular clusters, and we'll be talking more about this, is globular clusters tend to be older stars, okay? And globular clusters, remember we talked about the halo region of our Milky Way galaxy? Okay, globular clusters. So here's our galaxy. Here's the Milky Way galaxy. It looks like a frisbee, Milky Way galaxy. Then outside the galaxy we have the halo region, and we basically have globular clusters out there. All right. Open clusters are younger, and they are located not in the halo, but in the disk. All right, so I have a few slides on kind of looking back at when we talk about stars. One of the things about stars we'd like to know is the energy they're pumping out, and that's their luminosity. And we can get luminosity of a star because we can't visit the stars, but if we know how bright they appear and if we can get a fix on the distance, we can use one of those equations we looked at before to knock out luminosity. So we said a little bit ago that how luminous are stars? Well, they vary from 10 to the negative fourth to 10 to the sixth times the luminosity of our sun. And here's where I want to superimpose on this thing. I want to go ahead and tell you that those very, very low luminosity stars are running about the lowest threshold that a star can be with regard to mass. Now again, that big M, sorry, it's not absolute magnitude. That actually is mass. Okay, 0.08, what we say solar masses, are 0.08 times the mass of our sun. Those really luminous ones are 100 times the mass of our sun. I think I said in my slides, actually, even though we say that's an upper limit, we do see stars that are 150 solar masses. Okay, but that's kind of weird. Okay. So how hot are the stars? Now this would be the surface temperature of the stars. Remember we said the coolest ones, okay, are about 3,000 Kelvin, and the hottest ones are about 50,000 Kelvin. Okay, and then all I did again was to say that the coolest ones are the lowest threshold, and the hottest ones are that. And actually we could go ahead and give it a spectral type, right? These would be what we call M-type, and these would be O-type. O-type. All right. And then how massive are they? Again, you know, about the lightest one that can actually become a star, 0.08 solar masses. The heaviest one, about 150 solar masses. So how long do they live? Well, our sun, like I said, once it arrived at the main sequence, it knew it could do that for about 10 billion years. It's about halfway through, which is kind of fun. So what if instead of one mass of our sun, we looked at a star that was more massive? It had 10 masses of our sun. What would its life look like? Based upon what I told you, I said if it has more mass, it's going to live shorter. I know it seems kind of strange. But instead of 10 billion, it's going to live 10 million years. And that's just kind of the math to show you that. So instead of 10 billion, it's 10 million. Drat. Okay. Well, let's go the other direction. Let's take a star that's lighter than the sun. Let's say it's got 1/10 of the mass of our sun. How long is it going to live? Well, if it's lighter, it should live longer. Okay. Well, yep, it'll live longer, and you're talking, instead of 10 billion, 100 billion years. So one of the things we talked about in here, I said two numbers to know is 4.6 billion years, BY. That's the age of our solar system. And then the other number I want you to know is about 14, is it 14 point, oh, I might be butchering this. I'll just leave it at 14. 14 billion years, that is actually the age of our universe. Okay, so if our universe is 14 billion years, and these light stars can live 100 billion years, so you see where I'm going with this? Basically, there are light stars that have been ticking ever since the beginning of our universe. I think that's pretty cool. Okay, one last slide with HR diagrams. All right. So this is an HR diagram for the Seven Sisters. The Seven Sisters and Pleiades, that's the same thing. Pleiades and Seven Sisters. Remember that thing with nebulosity? Okay. So notice this set of stars were all born about the same time. And scientists get real excited about this. I don't blame them. This is a scatter plot, okay, where they're basically putting all those stars up on an HR diagram. Can you see these guys? Those high mass, stars, they are actually leaving the main sequence. And that's how it's going to go. In fact, to emphasize that, I would just say first. These high guys first. These are the most massive. They are going to leave the main sequence first. And they're going to kind of peel off. So actually that is kind of nice. It gives scientists kind of a nice way to gauge a cluster of stars. So I hope you can see the colors here. Purple, blue, and there's another blue with kind of a different symbol, darker blue. There's a tan here, okay? The different colors are all different clusters of stars. Okay, so like I said, a cluster of stars were born about the same time. But do you buy this? Can you see where that tan one, like this one right here, can you see where basically all of these guys have peeled off? And so this actually is the oldest. That's the oldest cluster up there. Why? Because all those other guys have peeled off. Okay? What's the newest one? Well, I'm kind of liking this one up here. This one right here. This would be the newest cluster. Okay? Why? Because it's got, even the heavy ones are still kind of churning away on the main sequence. So what we're actually talking about is something what's called a turn-off point. Their turn-off point is basically kind of the most massive star that's still clicking away on the main sequence. Okay? So the higher up the turn-off point, the younger the cluster of stars. The lower off the turn-off point, the older the cluster of stars. I think that's cool. All right. So I don't know what you want to do about your stuff and stuff, but because we'll probably, after the video, come back here. Unless you'd be easier to stay in there. Do you have a preference?
Let's decide when we figure out the temperature in that room.
Okay. Deal.